Thank you, Sergej. So good morning and thank you all for coming. So I'm going to talk about fractons and I just made this thing in my computer and you can see that there are two spelling mistakes. One is fracton and the other is my name, right? So, okay, so I'm going to discuss this area of fractons. So I hope that folks behind can see. This is good? Yeah. Okay. So I'll sort of divide this into three parts. So the first section is going to be what and why. Okay, and the second section is going to be lattice models. And the third section is going to be what we call as tensor gauge theories. Okay, and we'll cover this today and this in the second lecture. Okay, so that's the plan. Okay, so just before I started, people told me that they're from slightly different backgrounds, so they wanted to give me a small introduction to what the field is and where this connects to the field. Okay, so let me just give you a brief view of where fractons came from and what the current ideas are. Okay, so if we look at what has happened in condensed matter physics for the last, let's say, 20 years, there has been a lot of motivation to study not just material systems, but also synthetic systems. Like you can make interesting systems with qubits, you can make them with light, you can make them with variety of synthetic platforms. So this has motivated people to study a variety of problems which were not accessible in typical material systems. And this led to a question of what if my UV, that's ultraviolet, is described by, it can be described by bosons, fermions, or qubits, and so on. So I have some ultraviolet where I have lots of degrees of freedom, and I can create systems where they interact in a certain way and so on. And the question is the following. So suppose I'm in some d spatial dimension, right? How do I classify the phases that I get? Right? So if you take the elementary example of, if I take atoms interacting with each other, we typically know that, we have three phases: solid, liquid, gas, etc. So similar question, if I start with a bunch of degrees of freedom, the UV, they could be any of those or whatever you can imagine, and then you let them interact, what are the distinct phases you can get? So this is a question that has been posed. Right? So the question is of classification of phases. Right? Now, why did this question come back again? Because if you go back and read some of the condensed matter literature in the, let's say, 80s, 90s, and so on, this question was assumed to be solved in the sense that symmetry and Landau's ideas of classification of phases by symmetry was thought to cover everything. Then the quantum Hall effect was discovered, and the rest is history, as they say. And we now realize that Landau's ideas are not well, at least in the way they were stated, they are not enough to describe all the phases. And particularly quantum phases, the main concept that has entered the classification of quantum phases is that of entanglement. Right? So this is the main idea now. So if I were to be a little bit more concrete about this, if I have a system of some set of interacting qubits, I will say that the two phases that these large number of qubits realize are the same if, very crudely put, they have the same kind of pattern of entanglement. Right? So how can I distinguish between patterns of entanglement? Okay, so I'll just give an operative definition. Okay, you have to change it for perhaps a little bit for those kind of problems, but it will certainly work for qubits. So the idea is the following. So imagine that I have a quantum phase described by some ground state 1. Okay, and I have another quantum phase described by ground state 2. So these two are considered as the same quantum phase, right? If you can go from this to this by a set of transformations, which is called a finite depth unitary circuit. Finite depth circuit can take you from this to this, right? So if you can do that, then they are in the same phase, okay? If you're not familiar with this, I will give examples of this as we go along. So that's the idea. So this will capture this statement that the pattern of entanglement is same in both of them. Their details may be different. In detail, they're different, but the large scale pattern of entanglement is the same. So that's the idea, okay? So this is the background, and based on these ideas, a classification of phases is now available, particularly in 1 and 2 dimensions. And the challenges, the sort of what people are thinking about is what are the ways to classify phases in 3 dimension and higher dimensions, okay? And in that context, I'll just mention a few things about 2 dimensions. Let me first give you a statement about entanglement itself. So you see, the phases can be classified using entanglement in sort of in a very simple-minded way, which is the following. There are what are called as short-range entangled phases. Right? And there are what are called long-range entangled phases. Okay. So examples, I'll just work with examples. Examples of short-range entangled phases are these famous fermionic topological insulators. So typical example of that is like topological insulators. Right? So if you look at long-range entangled phases from the experimental perspective, it'll be like some fractional Hall state or something like that. That's a long-range entangled phase. So something like fractional Hall. Or as you will see, what I'll discuss at length today is things like Toric code and so on. Right? So these are examples where you find long-range entanglement. So what happens is, in these class of, these class of system particularly have been studied well in 2 dimensions. And based on these ideas of short and long range entanglement, a lot has been understood about classification of phases in 2 dimensions. Okay? So now what has happened is, in the motivated by a variety of things, which we'll come to, so around, I would say, let's say 2010 onwards, right? People started thinking about models and systems in 3 dimensions, and they discovered phases which have the following character. So the first is they have a ground state which is very highly degenerate. Highly degenerate meaning that you will see that this has sub-extensive ground state degeneracy. I will explain what this means in the lecture. So GSD stands for ground state degeneracy, right? It is sub-extensive. You will see that, okay? And then you will see that these phases, they will have, at least the models that I'm going to show will be gapped. They will have gapped excitations, but you can have these gapped excitations which cannot move, right? They're just stuck, right? So I'll call it fractionally mobile excitations. Right? Fractionally mobile excitations, and this is how the name Fracton shows up. Okay, so this is the idea. So this is the background, and these have posed new question to classification and all of that stuff. Okay, so I'm not going to go into the formal theory of all this. What I'm going to do is I'm going to take a view of just very elementary models we will construct, and we will look at some of the physics that comes out of it. So rather than give a sort of broad overview of some concepts, I will try to work with specific models and extract do some detailed calculations and find some answers. Okay, so that's the strategy we're going to use. I also have to add a very important point here. So many of these things that I'm going to discuss, I'll be primarily discussing these ideas. There are also newer ways to think about them. So for example, the Toric code, now we understand that there's a one form symmetry and there is a more sort of exotic picture of that. I will not discuss that in great detail. I'll just mention it as I'm going along because I'm sure that there'll be other talks in the school which will discuss that at length. Okay, so that's what we're going to do. So this is the background, and this is where this is where this fractons come in, right? So in terms of like where they fit into the classification picture, etc., they're a new kid on the block, and we have to deal with this. So that is where we are. Okay, so this is the background. Okay, so what is a good place to start? A good place to start is something that I think many people will be familiar with. So I'm going to start with the lattice models. And I'm going to just introduce the model that I'm going to use to illustrate the idea of fractons, using it, starting from a two-dimensional model, which I'll assume that many people are familiar. Okay. Okay, so what I'm going to do is I'm going to start discussing this model. So it's either called the Z2 gates theory, or in some limit, it will also become what is called as the Toric code. Okay. So let's see what this model is. So what I have is, I have a square lattice. Okay, so that's my square lattice, and I'm going to have Lx times Ly sites. So there are Lx sites this way, Ly sites that way, and there are periodic boundary conditions. Right. So that's my lattice. So where am I going to place my qubits? So my qubits are going to sit at the edges of these elementary plaquettes, right? So this is where my qubits are going to sit. Okay, etc. Okay, so those are my qubits. Okay, so if I have this many sites, you will see that there are Lx times Ly sites. So associated with each site, you have 2 qubits. So the total number of qubits is equal to 2 times Lx Ly. Okay, right? Okay. Now what I'm going to do is, I'm going to construct a Hamiltonian on this system, and just to introduce some notation. So there is this site will be called S, and the qubit will be labeled by some capital I, like this. Okay. All right. So now what I'm going to do is, I'm going to construct a Hamiltonian. So the Hamiltonian will be this. This is going to be sum over all the plaquettes. So let me label the plaquettes. So that's a plaquette, right? And I'm going to write down a term which is called as BP. So what is this BP? So if you take this plaquette, you see there are 4 qubits touching this plaquette. 1, 2, 3, 4, right? So 1, 2, 3, 4, right? So this BP is defined like this. BP is product over all the qubits that are touching the plaquette. That's my notation. I/P means I touches P, right? Of Zi. So what is the Zi? So I have this qubit Hilbert space which is 2-dimensional, and there are Pauli operators in this qubit Hilbert space. At I, there will be Zi and Xi. Those are the only ones I'll need for my discussion. So there are these things, and this product of these Zi's is the BP. Okay. All right. So if you stop here, this is just a classical Hamiltonian, right? Because everything commutes with itself, and you don't have to worry about anything. So the first question we ask is, what are the symmetries of this Hamiltonian, right? So what symmetries do we get in this problem? So you will see that if you ask what the symmetries are, then you will see that I can write down a term. So I'll just redraw that figure very quickly here. So this is the site S, right? I have this, and I can define a term which is called as AS, which will be product over all I that touch S, right? So this is the 4 things that touch S. And what I'll do is I'll use the X operators, right? So now you'll see that the Hamiltonian I've written down there, the H I've written down there, that will commute with every AS. With every AS, right? So S will go from, let's say, 1 to Lx times Ly. Because there are n Lx times Ly sites, it will commute with every one of them. And there's a very simple way to see this. So you see, you just imagine what you do to this placket. If I take this placket and apply the AS operator, it will do 2 flips. This Zi will go to negative Zi under the unitary transformation or in the process what I've written there. And this will also go to minus Z. And those 2 minus signs will cancel and this BP will be invariant. Okay, so that's the statement. Okay, so now if I want to give some quantumness to this problem, what I do is I define a new Hamiltonian. So this is the Z2 gates theory. And then I just put a transverse field on every side. So if you view this as a gauge theory, this is called as the magnetic term and this is called the electric term. Okay. And you can see that this don't commute with this. So you can see in general that BP xi is not equal to 0 if I touches P. Right. So this is the all right. Now I'll just make a quick jump and insist something which you can check later. So if H is much less than J, then you can get a apparently simpler Hamiltonian out of this. And this is called as the Toric Hamiltonian, right? And this for the students is left as an exercise. Right? In this limit, you will get this Toric Hamiltonian, and that will be this. Okay, so this is the statement. So what I will get is I will get this BP term which I had, the whatever term I had originally, and this fellow will show up as AS. So you can see that 4 x's are involved in getting to this AS. So you can see that this will go as something like h to the 4 by j cubed or something. That's what you can show that. Okay, so you can work that out later. So this is called as the Toric Hamiltonian. And this is the Hamiltonian which was proposed by Kitaev as a quantum memory. And we'll see why it was proposed as a quantum memory. Okay, so what we're going to do first is we're going to visit the ground state of this Hamiltonian, right? So you'll see it will satisfy the following conditions. H Toric code BP is equal to 0. So this BP commutes with this. H Toric code AS is 0. So of course that just comes from the invariance. Okay, and so you will get these 2 results, right? So everything, these 2 terms commute. So I can simultaneously diagonalize the system. I can find all the states. The states are labeled by the eigenvalues of BP and AS. Okay. All right. So all I have to do now is to find out how is the Hilbert space broken up into different energy eigensectors. And what I'm going to ask is, if I'm going to go to the ground sector or in fact any other sector, what is the degeneracy of that ground sector? That's what I'm going to ask. Okay, so this is the question I'm going to pose. Okay, to pose that question, I have to make 2 important observations to make the point. So the first observation is, you'll notice that BP are not independent. So product of BP has to be 1, right? So that comes from the fact that, so if you take a placket, it will neighbor other plackets, right? So if I take, for example, the product of these two BPs, the Z operator sitting here will square to 1, and you will just get this sort of thing. And if you keep doing this, it will become 1. And the same thing with AS. Okay, so you'll get these two constraints. So what am I going to do to do the second? So I write the second one also. This is product over S, AS equal to 1. Yes? Okay. Now what I'm going to do is I'm going to do a counting of states, right? So you will see how many independent BPs are there. So there are only Lx times Ly minus 1 independent BPs, right? And how many independent? So there will be Lx, Ly minus 1 independent ASs. Okay? All right. So the dimension of the Hilbert space in the way we computed this is 2 times the number of qubits, 2 to the power number of qubits. So that is the dimension of the Hilbert space. And you see, each of these things, BP has also the property BP square equal to plus minus 1. BP is plus minus 1, BP square is 1, and AS square equal to 1. So BP can take eigenvalues plus minus 1, AS can take eigenvalues plus minus 1, but there are only Lx minus Ly independent values for those. So you can see that if you label the states by the eigenvalues of BP and AS, right, any such labeling will have the following degeneracy, which I will write down. It will be 2 times 2 Lx Ly divided by the number of distinct values of BP, which will be 2 times Lx Ly minus 1. So this is number of BPs, if you like, distinct values, and 2 times Lx Ly minus 1. Right? So you will see that this becomes equal to 4. So you will see that the ground state now has a degeneracy of 4. Right? So this is a very important property of the Toric code. It has a ground state degeneracy of 4. Okay. Now you might think that this is very special to the square lattice that I've done. So let me just quickly show you this. So if you are not interested in the square lattice, but you just construct some amorphous lattice like this, like the one that I'm showing here, right? I don't have a pointer, but I think you can see. So what I've done here is I've just thrown a bunch of points. So those are the green dots here, like this. And I just do a Voronoi construction, right? And so you'll get these cells. You just put a qubit on every edge, and you define AS as, coming, if you go to this point, just take the product of these 3 X operators, that will be the AS. And if you take that cell, just take the product of Z operators on all of them, you will see that that is the BP. You can define exactly the same theory, and you can show exactly this ground state degeneracy of 4 by using Euler's theorem. Right? So if you put this on a torus, there is the, you can count the edges, vertices, and faces are connected by Euler's equation, and that will allow you to get this degeneracy. So the important point is, this degeneracy has absolutely nothing to do with the square lattice. It has got to do with this structure of the theory. Okay, yes.
So where are you putting the information? It is for a ground state?
No, this is the way I have constructed this. This degeneracy is true for any energy state. So in particular, it's true also for the ground state.
Okay. And also, like what I understand, like these are like some electric field and magnetic field. So there should be some Gauss constant. So are these like product of BP equal to?
Yeah, I'm slightly not okay. So if you work with this theory, then typically you will work in the Gauss law sector of AS equal to 1.
Okay.
This theory is theory by, you can think of it as a theory by itself.
Okay.
Right? And yeah. Okay. So you can think of this as some operator which can take plus minus 1 values.
Okay. Okay.
So in the ground space of this will correspond, ground space of AS operators will bear AS equal to all 1, will correspond to the Gauss law sector of this gauge theory. Okay, so this is the counting. Now I revised this because I'm going to use exactly such an elementary counting. So by the way, this 4 can also be obtained by much more sophisticated ways, which we can maybe discuss offline. But yeah, so I will use this kind of counting for when I go to the Fracton to show the interesting stuff here. Okay, so this is what I want to show, and I'll just make a quick connection to this one form story. So you can see that in addition to all the commutation relations that I have said, you can take the product of Z operators on any closed loop, and you will see that's called some Wilson loop or something. That will also commute with the Hamiltonian, and that is the starting point of connecting this to some one-form symmetry and all that. And I'm sure that there'll be other talks, so I will not go into that direction. Okay. All right. So let me quickly show you let me write down explicitly the ground state of this. So in the ground state, I need all the BP to be +1. Okay, I have to make an assumption here, right? So I'm assuming J greater than 0 and K greater than 0. So all the BP has to be greater than 1, and all the AS, all the BP has to be +1, and all the AS have to be +1. So if this is the ground state, then I can start from the following state. So what is the state I'm going to start with? I'm going to start from a state like this, right? So this state is equal to product over all qubits, right? The state that is, so this state will satisfy the following condition. So that is the +1 eigenvector, the eigenvector corresponding to the +1 eigenvalue of xi at every qubit. Okay, so this is the state. I start with this state, right? And this state will automatically satisfy AS equal to 1. Correct? And from here, I can write down the ground state, which I'll do on the other side of the board. So I can write down the ground state. So that will be product over all plaquettes 1 plus BP acting on that, say, let's say the X polarized state. Okay. So what this will do is AS is already 1, so we don't need to worry about AS. It will project out all the pieces of that state, which will give you BP not equal to +1. So that's what it does. Okay. So this is the ground state of the system. Okay. So is there any question, or I assume that these things are fairly familiar to people. All right. So I'll just mention a couple of things which will become important. So what are the excitations of the system? Yeah. The other 3 states. So, okay. So maybe I should tell how to get the other 3 states. Okay. All right. So thank you, Andre, for that question. So let me explain to you why there is a degeneracy of 4, and that will also allow us to write down the other 3 states. Okay. All right. So I briefly mentioned this. So I said that there are these loops like this, right? I mentioned there are these loops like this. Okay. So it turns out that there are more interesting loops that commute with the Hamiltonian, which are not products of these elementary squares, right? So let me show you a couple of those loops. So I put the system in periodic boundary conditions, so that can be thought of as a torus, right? So now what you do, you take the product of Z operators on a loop like this, right? So if you call this the X direction, there is some operator called as Wx, which I take the product of all this I on this line, Zi. Okay, so this will commute with that. This operator will commute with the Hamiltonian. And similarly, there is another operator which is called as Wy. Right? So this object is called wy. So that is, let's say I on x, and this will be I on y, and zi like this. Okay. So now you'll see that these things will commute with each other. They don't have any problem. They'll commute with each other. So wx, wy will commute with each other. And they also commute with the Hamiltonian. Comma y, I'll write both of them together. Okay. All right. And you see these things square to 1. So wx square equal to 1 and wy square equal to 1. Correct. That means I can simultaneously diagonalize these. So you can see that there are 4 possibilities here. Wx can take +1, -1. Wy can take +1, -1. And that's what gives you the degeneracy. Right? So this gives the degeneracy. Okay. Now I'll just insist this. You can check it yourself. This state that I've written down has wx, wy equal to 1. Right? So there are the other 3 states will have the other 3 combinations. So how do I get, if I write this down, how do I get to the other state? Okay, so that's the question. So these are of course called Wilson loops or Wilson lines. So there are set of other things you can do. So I'll just draw this like this. Okay, so imagine that this is the last of the thing, and periodic boundary conditions, and this connects to this. Okay, so I'll just identify this with, let's say, put a dotted line and identify with that. Okay, now what you do is you can construct another set of operators which are like this. So you flip, you take these links or these qubits, and you use the x operator, right? So this is x, say x1 all the way up to x lx or something. So those are called the 't Hooft operators of this. Okay. So we'll call them tx and ty, right? So what is tx? So tx will be, I will just simplify notation. I'll just say it's product over x along the, along the x loop, right? And ty will be product over the y, the x operators, right? Y would be, if I want to do the y, then I'll do something like this. I will take these things, right? So those will be the ones that go that way. All right. So what we will find is, you will find that these will also commute with the Hamiltonian, right? Of course, they're the product of symmetry generators, so that's not a problem. But you'll see that these things don't commute with those things, right? So if you take this, for example, so suppose I'll just give you an example. So suppose you take this one, right? You think of this as the Wilson line, the dashed one, as the Wilson line going along the y. That will not commute with the 't Hooft going on x, right? And because, in fact, it anti-commutes with the 't Hooft going on x. So what you can see is that the 't Hooft operator is the raising and lowering operator of the Wilson line. Right? So I'll just write that down. The 't Hoofts are the raising and lowering operators of the Wilson. Right? So that's the statement. So Andre, to answer your question, I can take this, I can hit it with one of the 't Hooft operators, say x, that will take me to wx equal to -1, and so on. Right? I can hit it with y to get the other 1 - 1 value, and if I hit it with both of them, I'll be able to generate all the 4. So that's how you can do this. Okay? It's good. Okay. Now I'll go to excitations. Okay, so to get an excited state, I take this ground state and I can do one of two things. You will see I'll produce an excited state, right? I can hit it with, I'll just hit it with plus first with this. So I will get an excited state. So let's understand what this will do. So you see, there is this interesting property we wrote down. Probably it's on the other side, but I'll just note this. So BP xi will be, this is anti-commutator. I'm writing it as curly brackets. This will be 0 if I touches P. Right, that you can just see. So if I take this xi and write the anti-commutator, that is BP times xi plus xi times BP, you will see that is 0 because this xi operator and the zi operator sitting there will anti-commutate. Right? So you can view this xi as a raising lowering operator of BP. Right? So what will happen? I start with ground state. These two BPs, all the BPs that are touching with this xi, they are 1. But when I hit this operator, they will change to -1, right? So this will give you a pair of monopole excitations. And the way we have constructed it, it will cost an energy of 4J, I think. Yeah. So the energy will be 4J. Okay. So let me show you this excitation for you on my computer. Okay, I hope you can see that. So you can imagine that these red things are like the state of the system in ground state, right? So I go and I click here, and you see what I've done is I've created a monopole, a pair of monopoles. They're adjacent to each other because you see where the pointer is, that's where I hit the xi operator. Okay, I do this. Now, what is the interesting thing about this is that, and this is where we will start moving away from, when we go to fractons, you'll see something else will happen. Okay, so you see, by doing local operations, I can move these away. So what I can do, I can take this, I can do one more flip here, I move this, right? And I can move this freely by doing just local operations, right? I can take this around and so on. So the important thing about this, these excitations is they don't have any constraint. They can be moved by local operations. Like a local flip will move the monopole from one side to the other, right? So this is a very important property of the Toric code, which actually ruins the Toric code at finite temperatures. So what happens is, you can see that since they are freely mobile, there is no energy difference between the two of these monopoles when they're nearby or when they're however far apart. So what happens is, if I pay an energy cost of 4J, I can gain a lot of entropy by just spreading these things out. And once these things are thermally excited, and if it's spontaneous, it'll start producing a lot of BP fluctuations in my system, and that will actually ruin all this ground state degeneracy and all this stuff, right? So this is a problem, because if your idea is to use this fourfold degeneracy or some version of it by putting open boundary conditions on one side, you can make this twofold degenerate. And if you want to get something called a surface code or something, then if you want to use this as a memory, then this finite temperature becomes a problem, right? Because then this kind of excitations can ruin that stuff. Okay, so those are the monopole excitations, and I can also just quickly show you I'll write down there in a minute. So I'll do R and then I go electric. Okay, so you can also get what I call as, this electric excitation. So electric excitations are excitations of AS, right? So what I do is, if I'm thinking of the Toric code, I can write down another set of excitations. So this will be something like Zi acting on the ground state, and this will produce a pair of, let me say, electric charges. Right, and you can see that you can move those electric charges freely. You can just, it's a simple thing, as you just keep applying these Z operators in a string and you'll just move them freely. So these are also freely mobile. Okay, so this is the sort of the structure that you get out of this Toric code kind of system. And to conclude the Toric code discussion, I'll make one final point. I won't be able to derive, will not have the time to derive any of this. And we will see that that will also have some important things when it comes connections to fractons. Okay, so we'll see that suppose I have some Toric code system like this, and I take some subsystem, let's say the subsystem is some A like this, and I compute the entanglement entropy, right? So the entanglement entropy associated with this will be proportional, some number proportional to the length of the boundary of A. So it will be like perimeter of A. That's this notation. And then there'll be another important term here, which is called the topological entanglement entropy. And in the case of Toric code, it turns out to be log 2. And again, it will be log 2, whether you use the square lattice or any of, you can use that amorphous lattice, it will still be log. Right? So it's truly topological in that sense. Okay, so this is what we usually call as topological order. And the topological order is sort of coming from the fact that there are these objects that commute with the Hamiltonian, and if you want to change the values of these, then you have to hit it with something like object, which is full, it depends on the full system size, this operator. And therefore, a local operation cannot change the values of this Wx and W. Okay? And this is why we call this topologically ordered, and it produces that entanglement. And I wrote down that ground state, this ground state. So there is another way to understand this log 2, and that is by looking at this ground state and realizing that it is a gas of loops, right? So if you think of these things as all spins pointing in some direction, and this BP, what it will do is it will actually flip spins on these plaquettes. So it will produce these loops. So there's a loop gas. So if you make a cut like this, you'll see that some even number of loop gas things have to go out of this area, and you can trace this log 2 to that. Okay, so that is where this structure comes. Okay, so this is the usual story of topological order. Yes, so are there any quick questions, or shall I move on to fractons? I guess we'll move on to fractons. Okay, so now what I'm going to do is I'm going to introduce a model which will be in 3 dimensions. Maybe I will start here, or maybe I'll start on the other side. So this model I'm going to introduce is what is called as the X-cubed model. Right. Also, I will discuss a related thing. I'll call X-cube Gates theorem. Okay. So what is this model? So this model is defined on a cubic lattice. And let's keep things simple for now. We will think of this with Lx, Ly, Lz sites along x, y, and z directions. And we will certainly impose periodic boundary conditions now. Right? And so what I will end up getting is, I will end up getting a system having these cube-like motifs. So there are these cube-like motifs. And I'm going to write down terms that are analogous to this BP, but in a different way. Okay? So the plaquette for me now is a cube, right? This whole cube is a plaquette. So I'm just going to call it C, right? To make it sound like cube. And what I'm going to do is I'm going to take these 12 spins. It's 12, right? Okay, I think it's 12, yeah. Have I got all of them? Okay, I think so, yeah. Okay, so there are these 12 spins that I have to use. And I'm going to define my BP is equal to product over all the qubits. So these are qubits. Product over all the qubits that touch this cube, right? So that is the magnetic term. Okay. So we'll just write the classical Hamiltonian, and then we'll work with that. So H is equal to minus J times sum over the cubes B cubed, right? So this is the starting point. So this is, of course, some classical problem. So I want to, of course, bring some quantum stuff into this. So I'll first try to find out what are the symmetries of this. Okay. So question is, what are the operations I can do that will leave this object invariant? Okay, this Hamiltonian invariant. So here's what I'll do. I'm going to draw. Okay. So you see here, 8 cubes are meeting. So this is the meeting point of 8 cubes. You can just see that, right? Okay. So what I'll think of this as some site. Okay. And you'll see that if I take, just imagine that this normal direction is x-axis, right? So let me call this x. I'm going to pick four qubits. That is this, 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 this. Now, what is the significance of this x? The 4 qubits that I've picked, if I were to draw like a square, making those with those as the corners, this x will be normal to that, right? And now what I'm going to do is I'm going to define a very similar thing that I did in the Toric code, which is why I went through that stuff. I'm going to call it AS, that is associated with the site S, and the normal x, right? And this is product over all I, and I will write Sx. Now Sx stands for all the links that touch the site S, such that the 4 of them, the plane that they make, their normal is x. Okay. All right. So this is xi. Okay. So if I now use this, and if I take this operator and ask what it does to some B cube like this, right? So if this is if this is the S, AS, and if this is the X, what it will do is it will flip these two. It will flip this. It will flip this and this, right? If this is X, it will flip this and this Z values. The Z will go to minus Z, and therefore this will remain unchanged. Okay? So, yeah. Oof. I'm so sorry. I'm sorry. Thank you. Yeah, that's Z. Okay. Okay. So this is so you can see that every B cube will commute with every ASX. So this will be this is so this you can think of like if you like some local transformation that leaves my Hamiltonian value. Okay. So this is one possibility. You can see immediately that there are other possibilities, right? The other possibility is that I can put this as the normal, and I can take these 4 of them, and I can construct I can construct similar things, like there are similar things like ASY and ASZ. Okay. Now you may think that there are 3 independent ones, ASX, ASY, and ASZ, but they're not independent, because you will see that if I take the product of these 2, this will turn out to be 1. Right? Because you will count each of these qubits, the X operators on those qubits twice. Right? They'll appear twice and they'll square to 1. So there's some kind of local constraint as well, right, on these AX operators. Okay, so now what I can do is I can convert this to what is called as an X cubed gates theory. How? I'll just take this and put the usual electric term. So now you see this Xi will anti-commute with the cube where if this qubit touches that cube. Okay, so that will give me the necessary interesting dynamics, or some quantum aspect will show up. So that is the X cube gates theorem. And if you ask what are the gates transformations, these operators are the gates transformations. Okay, so if people have not seen this before, if there is any clarification you need, please ask now. Otherwise, I'm going to do some manipulations with this. Okay, so this is the X cubed gates theorem. All right. Now, if I go to the other side of the board, we'll play exactly the same game that we played for the Toric code case. How am I doing with time? Okay. Okay. So what I'll do, I will do the following stuff. I will go to the h much less than j limit. And I will be able to convert this to what is called as the X cube model. Right? And that X cube model will go like this. Right? So there is a completely analogous thing you can do, what you did for going from the Z2 gates theory to the Toric code. You can do that for this X cube gates theory, and you can get this. Right? And you will see that here, this is like everything commutes with everything else. So we can find the ground state by simultaneously diagonalizing H with BC with all the A's. So what will this allow us to do? It will allow us to compute the ground state degeneracy in exactly the same way that we did for the Toric code, which is why we went through that in a little bit of detail. Okay, so what are we going to do? We are going to find out what are the constraints on BC, what are the constraints on AS, to find out how many independent BCs and ASs are around. Okay, and then we'll go through that elementary counting trick, right, of taking the Hilbert space and dividing it by the number of independent values of this. And that will give us the degeneracy associated with each other. Okay, all right. So I will show you I will go through the calculation, but let me advertise the answer. If you have not seen this before, then it will be very interesting. So you'll find that the degeneracy will go as 2 times 2Lx plus Ly plus Lz minus 3, right? And so let me just advertise what is the thing. So if I take log of this, you will see that it will scale as one of the linear sizes of the system. So if you put this as a cube, for example, where Lx equal to Ly equal to Lz, log of ground state degeneracy will scale as linear system size. So that is quite new in the sense that, we certainly did not know such phases 30 years back. Right? So these things were sort of discovered recently. Okay, so now let me show you that. That's actually quite instructive to do this. By the way, again, there are many different ways to arrive at that. I mean, there are very sophisticated math ways, but we'll do in very elementary ways. Okay. So the first constraint is product over C, BC equal to 1. That's an obvious constraint, right? You take all the cubes and multiply them, you will just get 1. You have no choice, because every qubit will appear twice and it will square to 1. Okay, now there are other constraints on this. So for example, if I were to just imagine, take a view of the cubic lattice from the x-axis, right? So what you will see is you will see something like a square lattice. So you can imagine now just drawing something like this and pulling out a slab, right? If you pull out a slab and multiply all the BCs on that, they will be 1. Does everyone see that? Right? So my point is, you see, so that's a slab, right? That's a piece of the slab. So you see, this thing is getting squared to 1 because, this qubit has, two of these cubes touching it, and so it will square it 1, right? So now you can ask, how many such things are possible? How many such conditions are possible? Yeah. So think of how many conditions are there for the, let's say that you take the slabs, which are the, let's say, YZ plane. So you're going along the x-axis. How many independent constraints are coming up? Lx minus 1. Because the last one will be generated by the BC equal to 1. Correct? So you will get that many. Okay. So I'll write down now. So the number of independent BCs. Yeah, if you could do all the counting very carefully, you will see that this is equal to Lx times Ly times Lz. Okay, I'll just remove all this. Minus Lx minus 1 plus Ly minus 1 plus Lz minus 1 plus 1. This plus 1 is coming from this constraint. Right? So these are the number of independent BCs. These are the total number of BC operators. And those are I'm removing the number of constraint terms, independent constraint terms, and that's what, so these are the number of independent BCs. Okay? All right. Next, we have to find out the number of independent ASs. Right? So now, if you look at any plane, if you multiply AS, say for example, the normal to the plane is X. If you multiply all the ASX, that will turn out to be 1. That's the same thing as what happens in the Toric code. Correct? So if you count that, it's a little more trickier than counting the BCs actually. You'll see why. Right? So number of independent ASs. Number of independent ASX, ASY, and AZ. If you take all this, you will find that the number of independent are the following, right? It will be 2 times Lx, I'll write down and I'll explain what this is. Lx, Ly, and Lz minus Lx plus Ly plus Lz minus 1. You have to remove 1. I'll explain why this is the case. Why do I have 2 times Lx, Ly, Lz? The reason for that is I can only choose Ax and Ay independent at every site. Az is coming for the right, because there is a local constraint that Ax, Ay, Az is equal to 1. Okay? And this Lx, Ly are the constraint that the products of Asx on a plane with normal x is 1 and Ay on the plane normal is 1. But when I take the Z, I cannot take the last layer with Z as normal, because that term can be written as product of all the other terms. Okay? And that is what removes this 1. Okay? I'll repeat it one more time. So this Lx is the number of the constraints on the, the Toric code like constraints on every plane with x as normal. We are treating them as independent. That's taken as independent. Az is A. So in this way of counting, Aszz is thought of as Asx times Asy. You think of it like this. So these will be independent. That will give you Lx, Ly constraint for each of those planes. Correct? And next is, what do you do with Az? So Az have also to satisfy those constraints. So if you work this out, you will see that the last layer of the last Z layer is actually already included in the previous, with all the previous constraints. So you have to remove that extra piece, and that is why you're removing the next one. Okay, so this is very, very simple counting, but you will be able to come up with the answer. Okay, so now you can see that if you just work this out, then you'll see that degeneracy is equal to 2 times 2 to the power, Lx, Ly, Lz divided by 2 times this quantity, 2 times Lx, Ly, Lz minus Lx plus Ly plus Lz uh, plus 2, right? minus 1, yeah, plus 2. So it will be plus 2, and the remainder is 2 times 2 Lx, Ly, Lz minus Lx plus Ly plus Lz plus 1, which is exactly equal to this result, which is this result. Okay, so this is a very interesting property of this model. It certainly was not known before these kind of models were discovered, that you have this kind of sub-extensive ground state degeneracy. So sub-extensive, because extensive would have been Lx, Ly, Lz. This is sub-extensive because it's coming as some fractional power of the system size. So it's like the number of qubits to the power 1/3 or something, number of sides to the power 1/3. So that's why it's called sub-extensive. Okay, what do we do with this? So the first thing is, we can write down a ground state wave function for this, right? So we'll write down a ground state wave function. So the ground state wave function is the following. So I start with the x polarized state, right? So that will satisfy all this. Okay, so of course this is of course for j greater than 0 and k greater than 0, right? So it will satisfy. So you want all of these to be 1, and you can certainly satisfy that by taking this x polarized state. And what do? I project out all the pieces that have BC as -1. So I just do this. So that is a ground state. Okay. So now let's try to quickly, the math will get a little tricky if you go into all this. Let's try to see what are the things. Yes, please. Periodic boundary conditions in all directions. That depends, I think. I think it depends on how you terminate and so on. Whether it is smooth, rough. Yeah. Toric code also is exactly the same. If you keep smooth boundaries, it is not degenerate. If you keep rough boundaries, yeah. Yeah, all those things have been looked at in great detail. Okay, very good. So this is the state. And remember, how do I go to the other that many states, right? So you have something like this, two-like operators here as well. But let me tell you how to think about the Wilson-like operators. So the Wilson-like operators are some things like this, right? So you take the cube. Sorry. You take the cube, and you just take you just go along a line. You take all the Z operators on that. You see that will commute to the Hamiltonian. So there are like large number of Wilson lines, and if you just count the number of Wilson lines, that will turn out to be like Lx times it will turn out to be that. But if you're not careful, you will overcount them. So you have to see that if I give you a Wilson line here, there are only a certain set of independent Wilson lines, and they will turn out to be proportional to Lx. The X Wilson lines will be proportional to Lx. The Y Wilson lines will be proportional to Ly, and Z will be proportional to Lz, and that's why you're getting those factors. So there is a very similar, the labeling of ground state using these Wilson lines. Okay, it's a little tedious to get into all the details, but that's the idea. So there are Wilson-like lines. Okay, sub-extensive number of okay. So that is the state. Okay, so you can ask a legitimate question now. So why are you calling this fracton? Right? So for this, I have to go to excitations. Okay, what kind of excitations can I produce? So this is the main story. So suppose I take the ground state and hit this with, let's say, the xi operator. Okay, so let's go to the computer and see what we can do there. It looks like a square lattice, but it's not. Okay, so that's the ground state. So I'm just drawing a picture of the ground state. Okay, so the qubits are in some state, and that's indicated by the red. Okay, so what I'm now going to do is I'm going to hit the z operator on some link, on some qubit. Let's see what happens. Okay, so here I do this. So you see, you have changed the state of 4 cubes. Those 4 cubes are, so if I flip this one, there is this cube, there is a cube that comes on top, there's a cube that comes northeast of this and southeast of this. So those four cubes have been flipped. Right? Everybody sees this? Okay. Okay. So now you see I've separated out of the fractons. Right? I've made all those guys. But for this, what did I have to do? Okay. So look at those blue dots. The blue dots is the operator that I applied. That's the product of all x's on those blue dots, on the blue links, right? So see if I can, let me see if I can show you this in 3 dimensions. Okay, so you can see that, do you see that there's like a membrane? So this blue stuff, that's like a membrane. So to create fractons and isolate them, you have to hit this with these membrane operators, right? So no local operations can move them. So if I try to move one locally, then I will leave the energy manifold. I have to go to some higher energy manifold. So there is no way to move these guys individually. Okay? So my first observation, excitation, is if I create an isolated cube, so an isolated monopole, is immobile. Okay? Immobile. So this is my first observation. An isolated monopole of this theory is immobile. To create an isolated monopole, I have to do a lot of work, which I did, like applying some membrane operators. And once if I get them separated out, then I try to move one of them, it's not possible to do in the experiments. Okay, so next question you can ask is, can I get any mobile excitations at all? Right, so that's the next question. All right, so I'm going to show you what's going to happen here. So let me say R, and let me do Z again. All right. So what I'm going to do is I'm going to create this, from the vacuum I can only create 4. So I create 4, right? Now you see something very interesting. So I can view this as a quadrupole of these monopoles. So this quadrupole can be thought of as 2 dipoles sticking together. Now what I can try to do is I can try to move the dipole. Okay? So you see what I'm going to do? I'm going to take this and I'm going to move the dipole. I move the dipole horizontally. I paid no energy. So the dipole moves horizontally, right? Now if you think about for a minute, you can also move the dipole. So I moved it along the x direction, say. I can also move it along the y direction. So watch this. Okay, so let me show it in. So you see the dipoles are in the same plane now. You can see. Right? Now I can move them around by probably doing this. Yeah. So now you see they have gone to a different plane. Right? So now if you think about a dipole, you can move the dipole anywhere on the plane freely. But only in the plane they were born in. You cannot take them out of the plane. If you try to take them out of the plane, you will create, you'll break the condition. So the statement is, dipoles are planons. Planons meaning that they can move in planes. Okay. Okay, so dipole excitations are planons. Okay, so this is a very interesting feature of the Toric code and of the, not the Toric code, of the X cube model, right? Okay, there is one more class of excitations. Okay, my graphics will not allow me to show that now. So let me try to tell you what those excitations are. I'll let the cat out of the bag first. Those excitations will be line-ons. They are excitations which can move only on lines. Okay, and so what is that excitation? I have 15 minutes, right? Yeah, 12. Oh. Okay. Yeah. You can give me like 5 extra. Yeah. Okay, I'll try to conclude. Okay. All right. So so what you can do is you can also hit this with the Z operator. Zi acting on ground state. So now, okay, so what happens? Let's just see what happens. So this is the story, right? So if I hit the Z operator here, it will change values of two of the things here. So if this is X, right? If this is the X direction, it will change the value of AX for sure. Right? No, sorry. It will change the value of it will change the value of the other two. It will change the value of AZ and AY. Because this link will go into definition of AZ and AY. Okay? So 4 of those will get changed. 2 here and 2 here. Now, if I try to move, so you can put those things as particles sitting here. They are the X electric particles, if you like. If you put those here, you can if you try to move that there, then of course it will create havoc. But what you will be able to see is that if you hit Z on this, you will move this here without any change, because once I hit 2 Z's on this, the AX, AY and AZ on these are back to 1. And on this plane, you will get AY and AZ to be -1. So you will see that these X charges can move only along X direction. And similarly, Y charges will move only along Y direction, and Z charges will move only along Z direction. So the electric charges of this theory, if you like, come in have three something, X, Y, and Z, and they will move only along those directions. Right? So they're called line-ons. Right? So these are the electric charges. Okay, so that is the summary of the fractonicity in terms of excitations of the X cube model. Okay, so now just to make sure that we have given the idea clearly. So this is not coming from some it's not something like Anderson localization, or it's not like some potential is holding these things together and so on. That is not the reason why things are not able to move. It is coming from the structure of the theory, right? The way if you like, the way the qubits are entangled, you cannot move this monopole from one side to the other because it has some long-range entanglement structure with the other things that have been created. So you cannot simply change this by moving that to the next one. So that is why it is a very interesting phase in terms of the fact that this is not energetic. It is sort of coming from the way the theory is constructed. Okay, now given the slight paucity of time, I will try to look at what are the things more I have to say. Okay, so the most important thing, I wanted to make 2 points. I will have only time for one. I will make the first point very briefly, right? So I discussed this idea of Toric code and all of that stuff, right? Okay, maybe I'll just show a transparency. That will solve the job. Okay. So I mentioned that 2 states or two ground states of systems are said to be in the same phase if you can do some unitary, finite depth unitary circuit. Okay. So there's a lot of literature on this. So the one that I'm citing is the one that I used for doing this calculation. So for example, I showed you that there is this amorphous Toric code and the toric code on the square lattice. You can show that you can go from one state to the other by a finite depth quantum circuit constructed out of C0 gates. And this arrow means that I'm doing a C0. So you take the state that I've written up there and you keep doing this. So in 4 steps, this will take you from a square lattice with some lattice parameter A to square lattice 2A. So what you'll end up getting is all the extra qubits that you have, they will turn out to be in some product, unentangled product piece. So you see here, so what this notation is, this orange things, I don't know if the orange is very visible, that is the part of this ground state, right? And after I do C0 on all the unit cells like in the way I've shown together, one shot, you will see that one of those qubits will get unentangled. So that's this up state, right? And then you do the C0 again between this, that stuff will get unentangled. And you keep doing this stuff will get unentangled. And after 4 steps, 1, 2, 3, 4, you will end up with this, where the orange guys are in the same state, which is the toric code ground state, tensored with all these qubits which are unentangled with it. So what I'm showing you here is that in the infinite square lattice, this ground state is a fixed point of this entanglement renormalization process. Right? Okay, so that's the statement. And if you want to show that the amorphous thing is equivalent to the square lattice, what you can do is you can identify some set of sites in your amorphous thing, which you will remove and do suitable C0 operations, and you can convert it to a square lattice times some unentangled qubits. Okay, so that's the way to show that these two are the same. Okay, now what happens when you do this with X cube model? So some beautiful work showed this. I'm not able to. Why is that not showing up? Okay. Yeah. Okay. So those are the. Sorry. Okay, something is not right. Oops, I don't have that here now. Okay, I'll make the point without the slide, or maybe I'll show the slide tomorrow. So what you can show is the following. So suppose you are seeing that there's a ground state degeneracy, right? So suppose I say that I have a system with 30, 30, 30. And I take a system with 31, 30, 30. I just add one more layer. So this looks like this is a different phase than that, right? So what these authors, Shirley et al., what they showed is that you can actually go from the 30, 30, 30 system to 30, 31, 31, 30, 30 system by taking a toric code. A toric code which is tensored with this thing. You can do a local finite depth circuit, and you can sort of take this toric code and stick it into this X cube model, and it will become the state of the X cube model. Okay, so this is called foliated Fracton order. So you can think of this X cube model morally as some kind of toric codes which are sort of nicely coupled with each other and so on. So what is the consequence of this is very interesting. If I scoop out some region of R times R times R, some cubic region out, you will see that it has an entanglement entropy which has the area law piece, of course, and a term which is proportional to R. So that term proportional to R is crudely coming from the fact that each of that gamma log 2 will just multiply, it will be proportional to R and it will contribute to the entanglement. So that's the sort of thing that comes up. Okay. So I wanted to just briefly mention this. Unfortunately, I screwed up with the slides. I'll show the slide tomorrow of entangled renormalization, or I'll show the slide in my talk, whichever is convenient. But I want to show one very important thing which will be useful when we discuss tensor gauge theories, etc. And that is the idea of duality. Okay. Okay. So now there's a very interesting result of Vijay, Hafu, etc., which I will mention now. So first thing is, I don't know if people are familiar with this or not, I'll just mention it. In case you're not, you should check this out. If you take the Z2 gates theory and try to find a dual model to Z2 gates theory, you'll find that that is the Ising model, the quantum Ising model on the dual lattice. Okay. So what happens with the X cubed gates theory? So this is what I want to show. Okay, and I'll quickly show you how to get the duality in a very inexpensive way. Which one? Toric code. In 2+1, right. Z2 gates theory on the square lattice. Correct, absolutely, yes. Yeah, so this, we start here. And so what we notice is that this has, so every BC commutes with every BC prime. Every Xi will commute with every Xi prime. And what else do I need? I need the following. I need that a BC anti-commutes with Xi if I touches C. So that is, these are the relations I need. So what you can imagine is that you can imagine that the X cube gates theory has some Hilbert space which we have written down, and there is some set of operators which satisfy this algebra. Right? So we can now ask a question, can I find a different Hilbert space and a different set of operators which will give the same algebra? Right? And that will give me the duality. Okay. So the idea is the following. You take the cube, and you construct the dual lattice to this cubic lattice. So you will get the sides of the dual lattice are the centers of the cubes, right? And you will get one here, and then there'll be that link and so on, right? And I need 4 of them, so I'll just draw like this. Maybe I should get this line correct. Like this, right? So that is, so there is a, so this one, this thing is at the center of this. Okay, let me draw it like this. Okay, very good. Okay, so what I have here is, this is the cube of my original model. These are 4 points which are sides of the dual lattice which are sitting at the centers of the cubes. And what I've done is, imagine that this is some link of my, my original cube. That link is centering this face. You see, I'm calling it face and not a plaquette because the qubits are going to be located there. It would be called a plaquette if the qubits are located at the centers of the links of the dual lattice. Thus, the qubits will be located at the corners of the squares of the dual lattice. Okay. So what I'm going to do is I'm going to construct a tilde, some operators with a tilde notation to show the dual operators. So the mapping is like this: B cube gets mapped to X tilde. Right, so the centers becomes the sides of the cubic lattice. No, so you see this B cubed was here, BC was here. That is mapped to X tilde. Okay. Now I have this operator Xi. So Xi is living here. That is where Xi is. So this is Xi. This Xi I'm going to map to the product of Z tildes on this, and this. So the mapping is Xi maps to, I'll call it as Fi. That's the face of the dual lattice, right? This is called the face of the dual lattice. So Fi by definition is the following: R product over Z tilde C, right? Now C are the sides of the dual lattice, C touching I, reverse, correct? So that's what happens. And you can see that these will satisfy exactly the algebra that you have. Correct? And so what I've done, I've mapped this Hamiltonian to J. So this is the dual Hamiltonian, H tilde. J sum, this becomes X tilde C minus K or H times sum Fi. So this model is called as the phase Ising model. And why is it called the phase Ising model? Because you see the Ising interaction comes by interaction of spins, the Z operators on 4 of these things. And that's the phase of the cube of the dual lattice. And every phase will contribute this 4 spin interaction. So what is interesting about this is that this model has a subsystem symmetry. So what you can do is you can take a plane of the dual lattice and flip, you can apply the X tilde operations on that. And that will leave the Hamiltonian invariant. So this problem has subsystem symmetry. So general thing that comes out of these Fracton kind of lattice models is that at least the ones that I'm aware of, if you take those models and construct their duals will be some kind of Ising kind of, some kind of elasticity model, if you like, if you call Ising as elasticity, with subsystem symmetries. So this turns out to be a very generic feature of these kind of Fracton models. Okay? So, I think I've run out of my time. Okay, so maybe I will show you the entanglement normalization tomorrow. So what we'll do tomorrow is we will change the flavor of the discussion. So this is our discussion of lattice models. So from here we have seen that there are explicit models in which you have these Fracton-like excitations which have mobility restrictions. What we'll try to do is we'll try to start from the fact that we have mobility restrictions in the theory, and we'll try to construct field theories which will weave in the mobility restrictions from the start. Okay, and those will be the ones that I mentioned. They'll be the tensor gauge series. So that's what we'll do tomorrow.
Thanks, Vijay. Quick questions.
Also exist in 2D?
No.
So what about this Ising placket model? Would you consider it as a fractons or?
No, so the formal standard statement is there are no fractonic models in 2 dimensions.
But in your definition, consider the Ising placket model in 2D.
Ising placket, like phase Ising model. That's not a fractonic model.
But this model does have this ground state, sub-extensive ground state degeneracy and also.
But it does not have immobile excitation.
I think my question was going to be along the same lines, which is that in 3 dimensions, this ground state degeneracy is locally stable.
Yes.
Whereas in 2 dimensions, it's locally unstable.
Right.
And so
you can add operators to kill that. What is being mentioned is, so you can ask this question differently, right? You can ask, why can't I take one layer of this X cube model and pretend that that's a 2D model? But you can add terms to that which will kill this, that respect all the necessary requirements. It's not stable. Right. Thank you.
Could you say anything about the role of translation symmetry? So the Toric code is a topological model. You can put it on any lattice. Obviously, for these Fracton models, that's really.
Thank you. I missed this. Very important point. Thank you so much. Okay. So the question now is, what kind of degeneracy is this? Is this like a topological degeneracy or not? So the answer is, we know the answer very clearly for at least a class of Fracton models called as foliated Fracton models, like the ones we construct by layers. So for example, you can take exactly the X cube kind of interaction. That is, what is X cube? What do I mean by X cube kind of interaction? If I take a site, or if I take a qubit, it has, if I take a cube, it has 12 interacting things and so on. So what you can do is you can construct the same thing with the Kagome. You can start with Kagome, and you can layer this up, and you can have 6 links coming out of every side, and you can construct a cube-like structure. But that will give you a different ground state degeneracy. It will be sub-extensive, but it will have different coefficients. So the word that goes with this is, it's called geometric order, not topological. So somehow it remembers the UV, right? If you take, for example, if you mentioned translational symmetry can be broken in two ways. One is I can make the J's random. So as long as I make the J's random and keep it positive, let's keep it positive, then everything will go through. So in that sense, formally you don't need translation symmetry, but you somehow need the translational lattice structure. Not coarse grained, right? I mean, it remembers the real UV, right? Because it remembers like what lattice it came from. Those coefficients will determine. So for example, if it is Kagome, it remembers that it came from Kagome.
More questions? Okay, I don't see any hands. So let's thank Vijay once more, and maybe you can catch him again.